and I am working on brain-machine interfaces. So today I'd really like to share with you my vision for how brain-machine interfaces can really bridge the gap between what's going on in our brains and allowing everyone to live full and independent lives. So what are brain-machine interfaces? Maybe we've heard about Elon Musk's new venture in Neuralink, which is also working on brain-machine interfaces. So I'm going to give a quick introduction to the field, what a brain-machine interface looks like, so we're all on the same page, as well as then taking a step back, looking at how the brain communicates with itself, how we measure these brain signals, current challenges in, and also kind of the future of what brain-machine interfaces look like. So as an introduction, some of the most common brain-machine interfaces in the last 10-20 years have really been geared towards allowing paralyzed people to regain independence in their lives. So here is a video of a woman who's been paralyzed for 15 years, and she has a brain implant located in one region of her brain, and she's using her thoughts to control this robotic arm to move the water bottle closer to her so that she can use her own thoughts to bring food, water, to reinitiate movement. So it's pretty amazing. So in addition to an external machine like a robotic arm, it's also been used to help with computer cursor control so that people can type, people can surf the internet when they're otherwise paralyzed as well. So we can see that she has also a brain implant located with an electrical cable connector coming out, going through a computer, and then going onto the screen so that she can do the typing herself. So she can email and she can text her friends as well. So what's really going on behind the scenes of these brain-machine interfaces? So I'm going to boil it down to, let's look at your brain, because that's one key component of your brain-machine interface. And again, like I mentioned, there are these implants located in the brain that are measuring your brain signals. So it's doing these measurements, and that cable connector that we saw kind of comes out, it's transmitting those electrical signals, and it's sending it to another computer. That computer really decodes the neuronal language. So they're speaking, and they're speaking how neurons speak, and we have to understand what it is that they're saying. So we can use a lot of computer algorithms, software, a lot of mathematical and neuroscientific models to figure out what it is they're saying, and then we send that message to the machine that the brain is trying to control, whether it's a robotic arm or if it's a cursor. And then finally, to really complete this puzzle and close this loop, both users, they were using their eyes to kind of feed back where the position is, whether where the water bottle is relative to them or where the computer cursor control is. So that's kind of feeding the information from the outside world back into their own brains through their eyes. And so really this is the basic framework for brain-machine interfaces. It takes from your brain to your machine and really just closes that gap right there. And it really helps a lot of these paralyzed people to regain movement. So if you think about it, as humans, we really thrive on communications and interactions with each other and with daily experiences. So right now, I'm speaking to you, I'm communicating to you with my words and with my gestures as well. And you guys are taking that information in through your eyes, you're watching me move, you're listening to me to speak, and you're really integrating all that information in there. And so that's really key to what the brain is. It's taking all these information in, and it's also outputting some sort of action, whether it's something concrete like a movement, or it's something less tangible. So maybe you're learning something like right now, or you've kind of take all this information in to make a decision. And so with brain-machine interfaces, I think it can go so much more than just controlling an external machine. We can also look into how can we use brain-machine interfaces to help regulate the brain a little more for people who suffer from neurodegenerative conditions, or perhaps they're paralyzed, or they have traumatic brain injuries. How can we fix it in the brain itself? So to get to that, we have to first look at how the brain communicates with itself. We have to understand a little of how the brain works. So let me take all this away, and we're just going to look at the brain. If we zoom in to the brain, we can see it's composed of these neural networks. So each of these green dots up here is a neuron. And your brain is composed of thousands and millions of neurons all connected together in really intricate networks. So here is a neuron right here in the lower, that's one single neuron that I've isolated. And if we take an illustration of it, we can see that kind of at the top it has all these inputs, just like your senses. You have many, many senses, and you take all this information in. You put it all together through the body, and then it kind of outputs some sort of action at the end of it, which connects to another neuron. And if we kind of look at the upper hand corner there, where it's connecting to another neuron, how neurons communicate is that it's taking in information through the chemicals that are being released from another neuron. It's taking that chemical information in, and it's kind of accumulating everything, aggregating everything as an electrical signal, and that electrical signal is then being transmitted down. So one thing I really want you to remember is the brain is not just electrical signals, which is one thing that we always think about. It's electrical and chemical signals, and it's really, really just fascinating, the symphony that your neurons are really kind of communicating in. So if this is how the brain communicates, for brain-machine interfaces, we want to know how can we measure these signals, because again, we're trying to decode the language that the neurons are talking in so that we can either translate them to the outside world or to help reinterpret them so that they're sending the correct messages. So here is your brain zoomed in. I'm going to add a skull here, and I'm going to kind of go over a quick overview of the different types of electrodes. So electrodes are sensors that can measure electrical signals. Later on, I'll talk about probes, and electrodes are a type of probe. And the reason I want to use the word probe later is because I want to also include chemical sensors. So again, the brain is just electrical and chemical signals. Brain-machine interfaces have largely been developed in the last 10-20 years using the electrical medium. So right now, I just kind of introduce the different types of devices using the different types of electrodes. So the one we might be most familiar with is EEG. So these are electroencephalograms, and they are electrodes that are placed on your scalp. And these are non-invasive methods. Next, we have minimally invasive methods, which are similar to EEGs, but they're placed right on your cortex, which is the surface of your brain. And finally, we have different generations of electrodes, such as the microwires, or different microelectrode arrays, or multi-site electrodes, which are implanted in your brain. So they're not just on your surface, but they're actually implanted in your brain. So let's go over a list of the pros and cons. You might be thinking, well, why don't we just use EEGs? Because they're the safest. We don't have to go into your brain at all. So EEGs, again, they're non-invasive. They're very safe. They're a great clinical tool. But the problem is that it's not something we can wear. You wouldn't expect someone to kind of go around with bunches of wires on their heads. It's not very practical. It's very easy to fall off. But then more importantly, we have very poor signal. Because remember, we're trying to measure these electrical signals not just through your skull, but there's also more tissue. And then finally, we reach your brain. So we have a very weak signal. So we want to go closer to the brain so we can get a better signal, really understand what's going on. So with electrocorticography, remember this is similar to EEG, but it's placed right in your brain. So this is great because we're close to your brain, we get a better signal, and we know what's really going on. But the problem is that you get this lunchroom effect, because remember, you're listening from the outside. So imagine someone's listening from the outside of this room. They can kind of hear what I'm saying. They can kind of roughly hear where I am, but they don't have a really good picture of what's going on. And the shocking thing is that even now in the 21st century, as neuroscientists, we really don't know what's going on at the biological and chemical level of your brain. We really don't understand so many things about the brain. And so that's really one of the motivations for having these penetrating electrodes that go into your brain. They're very, very risky, but there's so much huge reward in terms of understanding what's going on, and then for the future of brain-machine interfaces. So one of the the first generation of penetrating electrodes are called microwires, and they are literally just electrical wires that we stick near a neuron, so they're in your brain, in a specific region of the brain that we're interested in, and we just measure. So one issue is that maybe you noticed there are a lot of yellow dots on each of these sensors, and each of the yellow dots is an actual site that we can measure electrical signals. So one limitation of the microwires compared to the other previous EEG and ECOGs that I've mentioned is you can only measure one signal at a time. It's already very limiting. So that's why the second generation was sort of developed, these microelectrode arrays and multi-site electrodes. Very similar in concept, but we can put a lot more electrode sites on there. But the problem is, as you'll see, I have this huge table. I didn't really go into a lot of the pros and cons of them, but one of the things is I want you to bring you attention to the column of cons, where we see that all of these penetrating electrodes, they induce a significant tissue response, which I'll talk about more, but more importantly, the signal, the electrical signal that we're trying to measure, deteriorates with time. So essentially, these electrodes can't work for more than 1 year if we're lucky. In most cases, it's 4 months. Really, this will depend. We've had electrodes that can work up to 5 years, but like any sort of medical device, we want to be able to last decades, especially if it's implanted in your body. We want to be able to last decades. So the reason I bring up inducing tissue responses in that column is that really the signal quality that we're trying to measure and the tissue response, they go hand in hand. And sort of this third generation that neuroscientists and neuroengineers are working on for penetrating electrodes kind of addresses this issue. So we have really the third generation of neuroelectrodes which are working on flexible electrodes. And I'll talk soon about why we decided to go towards flexible electrodes. But first I really want to delve into why tissue responses are a significant issue. So a tissue response is just a fancy way to say your brain is, there's an inflammatory response. Your brain senses there's this foreign body in your brain and it wants to get it out because it's not supposed to be there. So let's take a close-up look of what an electrode looks like in your brain tissue. So here I'm using actually a chemical electrode, a chemical probe as an example, just to add a little variety in here. And so here we can see the blood vessels that are feeding the brain oxygen and nutrients. Imagine the white space is filled with all the neurons that I showed previously. And in addition to the neurons, I also want to introduce microglia and astrocytes, which are additional cells that are in your brain that are not neurons. And they have many, many functions. The ones we'll focus on today are on their inflammatory protective responses. And finally, I have neurochemicals that this sensor is trying to measure. So what happens with those kind of like the second generation, for example, electrodes or probes? Why is it that they fail after 4 months or 1 year? So one issue is that this is an ideal situation. The probe looks like it's really well integrated in there, but that's often not the case because right now probes are so large that they break this blood-brain barrier. It kind of prevents the blood vessels from feeding the brain nutrients and oxygen there. And additionally, the large size causes this a very acute trauma. So we see all these microglia, within a day, within 24 hours, they start adhering to the probe surface because they realize this is not supposed to be here. This is very traumatic. And then also over time, astrocytes, these big green astrocytes really accumulate to the surface as well. Again, because over time, if you think about it, right now you guys are all sitting perfectly still. But you guys are breathing, your hearts are beating, and your organs are all moving, tiny, tiny amounts, 15 to 30 micrometers maybe. But that little movement, if you have a rigid object kind of inserted into a soft kind of like jello, we'll think of your tissue as jello, that's going to tear that jello every little bit that you move. So even if you're perfectly still, we're going to have this micro motion effect over time, and it's going to cause a lot of damage in your brain tissue. And so as you can see, just in this illustration, it forms a physical scar sheath. So all these inflammatory responses, all your brain is trying to do is protect itself, but it forms this scar sheath where it physically prevents the electrode that's implanted in your brain from measuring the chemicals and from measuring the electrical signals. And this is kind of one of the main reasons why a lot of these electrodes that are implanted in your brain fail. So what can we do about this? First, I want to show you an image of what a scientist is looking at. So before, this is an illustration of what's going on, the biological processes. And then when I'm looking at these brain tissue samples, before we were taking, like, this is your brain, the electrode's kind of in there. Now we're going to just take a cross-section and look down. So in this black hole right here, you can see that's where the probe was located. And then you can see all the really, really bright green. And that's the astrocytes that I was talking about. This is about 4 to 5 months after an electrode has been implanted in the brain. And this is 4 to 5 months. We see huge astrocyte expressions, very bright green, as well as the bright purple is the microglia. So we also see a lot of these inflammatory responses. And like I had mentioned, the microglia is kind of caused by the acute trauma is caused by the largeness of the probe relative to the tissue. And then the green is really caused by the micromotion because it's so stiff. So this kind of leads to our answer of how can we design the next electrodes to better integrate into your brain. And this really leads to kind of cellular size flexible electrodes. And you can just see how small it is relative to the previous one and how much better it is integrated. And so again, I'll bring up this fluorescent stain image of an actual brain tissue sample with the larger, stiffer probes in there. And then here, I just want you to compare the difference with the same, it's also in there, implanted in there for the same amount of time, but we're using smaller, flexible probes. You can barely see where that black hole is because all of it is so much darker, and that's good. We want to see a dark, dark image. And just for reference, this is an image of an unpenetrated tissue, so we've never inserted an electrode in there. And you can just see that while there is still, it's the middle picture with the smaller flexible probes is slightly brighter than this image here on the far right. The improvement over the larger, stiffer probes is undeniable. We can just see that there's so much less damage after 4 months, and we also have a similar image that I haven't showed you that's at the 12-month time point that's also very similar, just very reduced responses. And this response really shows us, this reduced response really shows us it's better integrated in the tissue, and we also notice that our probe can function for that same amount of time. So we really see that the biocompatibility and the mechanical compatibility of our probes really directly correlates to their functionality and really their clinical viability. So previously I talked about brain-machine interfaces for just controlling machines. And I introduced this idea of what if we are not just controlling machines. So here's another brain-machine interface that came out recently called NeuroPace and used for epileptic patients. And what they do is that in epilepsy, what happens is that one part of your brain starts having abnormal, really, really large electrical signals that eventually leads to a lot of convulsions and your bodily physical convulsions. So what NeuroPace does is it has an electrode implanted in that epileptic region of your brain, and every time it detects a seizure going on, before that seizure can transmit to the rest of your body, it sends another electrical signal that stops that seizure. And this has been life-changing for people for who like the drugs do not work and they're not candidates for surgery. And this brain-machine interface is really actively stopping these seizures. Similarly, we have deep brain stimulation, which is another type of brain-machine interface for Parkinson's patients. In Parkinson's disease, they have a depletion of the neurochemical dopamine. And what happens is that what this deep brain stimulation is that an electrode is implanted either the substantia nigra or the ventral tegmental area, which are known regions. If you put an electrical stimulation in there, dopamine the dopamine imbalance gets kind of raised up again, and then people have significant reductions in their tremors and other symptoms as well. And so these are just two existing examples of where brain-machine interfaces can go. So instead of controlling a machine, I want to talk about how can we use brain-machine interfaces to help regulate your brain, to balance these electrical chemical activities, which are really at the heart of just a well-functioning, healthy